So in the last lecture we proved a result about difference. We proved that a way to generate the different ideal is as follows. You look at each element in the bigger field which is an algebraic integer and generates the bigger field over the smaller field. You look at minimal polynomial of each of those and take their derivatives, compute them at the respective elements and take the ideal generated by that. So let me recall that for you here, whatever I said in words. So S is set of all alpha in OL such that L is K alpha, and then the different of L over K is phi alpha prime of alpha such that alpha, so this is the ideal generated by this set, right, where phi alpha of x, so where phi alpha of x is the minimal polynomial of alpha over k. Okay. All right. So as I said last time, it looks like this is a may not be of practical use, but it has theoretical application, and so what we are going to do is we are going to prove the following. So let L over K be an extension of number fields okay, so it's a finite extension. Let P be a non-zero prime ideal in OK, and capital P divide small p. So capital P be above small p inside L. Okay. Let E be the ramification index of P over P. So this means that when you, so let me recall for you what this means. This means that P appears to eth power and then there are some other terms. Okay, so that's the ramification index. Then P to the power E minus 1 divides the different of L over K, right. So this, so E could be 1, right. E is just that P appears in the factorization of small p, but it could appear to the only the first power. In this case it means that I mean this statement is contentless, but if capital P does ramify, then it means that capital P divides the different, okay, and P to the E divides L over K if and only if P divides E. I mean E is an integer, so this simply means that the rational prime below small p divides your E. Okay. All right. So this means that if something, so if E is equal to 1, then P to the E minus 1 is the largest power of P dividing the different. It means that P does not divide the different. Okay. All right. So let me give a proof of this and then we will discuss its corollaries. P of OL, this is P1 to the E1, P2 to the E2 up to PR to the ER, and here P1 is equal to P and E1 is equal to E, and then other things are just what they are. So suppose alpha belongs to Pi, okay, for some I, and let phi I of x in OP of x be the minimal polynomial of alpha as an element in O sub pi. Okay. Then as we did last time, every coefficient of phi I of x except the leading one, except the leading one is divisible by p, is divisible by small p. Okay. So what this means is that so in particular this means that the coefficient of the one next to the leading one is also divisible by small p. So hence what we have shown is that alpha in pi implies that p divides a trace from LPI to Kp of alpha. Okay. All right. So this is just some claim that we proved, and we are going to use it in our proof of the theorem. So what do we want to prove? We want to prove, so we want that p to the e minus 1 divides the different, right. This is same as saying that that the different ideal is contained in p to the e minus 1, right, which is same as saying that p to the 1 minus e is contained in the different inverse. Right. As I have said again and again, it is easier to work with different inverse because that has a more explicit definition. So that is what we want to do. So we want to show this, that if you have something in p to the 1 minus e, then it is contained in different inverse. So you let beta belong to p to the 1 minus e, and we will show that beta is actually inside the different inverse, right. Okay. So let pi be an element in p but not in p square. So such a thing obviously exists, and you consider pi times beta. Okay. So you see that this belongs to p times p to the 1 minus e, but p itself is contained in p to the e. So this is equal to p, hence pi beta is in p. This means, as we just showed, as we just proved here, let me number it. So this is star, let us say. So this means by star that trace from let me write it directly as L to K okay, let me not rush, and let me just say that this trace of pi beta is inside small p, but you see that pi beta, this belongs to p to the 1 minus e, which is also contained in pi into p to the 1 minus e for all I bigger than or equal to 2, but that thing is contained in pi. Okay. So therefore trace from LPI to Kp of pi beta is also inside P. Okay. And now we know that trace from L to K of pi beta. So, from before we use that this is summation I going from 1 to R, trace from LPI to KP. So, we proved this before that the global trace can be computed by local trace of all places above a fixed place, and so this belongs to P. Okay. So, what we have is that excuse me. Oh gosh. Trace L over K of pi beta, but you see pi is already in L, already in K. So, this is simply pi trace L over K of beta is in P, right. This means that trace L over K of beta is inside OK. We write it like this, it's inside OP. Therefore, beta is inside dl over k inverse. Okay. All right. Yeah, no, I think this was right, and this is what I need anyway. Okay. So hence p to the 1 minus e is inside dl over k inverse, and p to the e minus 1 divides the different ideal. Okay. So, so we proved the first part, that p to the e minus 1 divides the different, but now we want to know if some bigger power of p divides the different, and we said that p to the e divides the different if and only if p divides e. So, let us prove that, and we are basically going to redo the same argument, we are just going to be a little bit more careful. Okay. So, now next we want to find when p to the e divides the different. Okay. And what did we use earlier? So, in the first part we used that alpha belongs to pi implies that trace from LPI to KP of alpha is in P, right. And so, we no longer want to do that, because this is what reduce the power of p dividing the different by 1. Okay. So, now instead what we do is we start with alpha in OL and let alpha bar mod p be so let alpha bar be the image of alpha in OL mod capital P, right. Okay. And as before, there is a lot of repetitions in all these proofs, so I am not recalling the notation again and again. Consider phi x equal to minimal polynomial of alpha in OP over O small p. Okay. So, we know that phi bar of alpha bar, so where phi bar means phi modulo small p, alpha bar is the root of that. Okay. And let psi of x inside O mod O OK mod p of x be the minimal polynomial of alpha bar yeah. Okay. Then psi of x divides phi bar of x because it is the minimal polynomial. Okay. But what is the degree of psi? The degree of psi is f, this is the residue degree of p over small p. What is the degree of phi bar? This is E over f, right? Yeah. Okay. And now using the fact that okay, basically Hensel's lemma, let me just go back a little bit, yeah. So again, yeah, there are things to verify, so let me do this as an exercise. So use Hensel's lemma to show that phi bar of x is psi of x to the power e. So all you have to show is that phi bar of x is a power of psi of x, and if you know that it's a power, then it will be to the power e, right? Because you just match up the degrees. All right. So now if you yeah, so if psi of x is x to the n, maybe n is a bad letter to use here, x to the t, no, it has degree f, so I should use f, plus a1 x to the f minus 1 and so on up to a0, then psi of x to the e, this is x to the f plus a1 x to the f minus 1 and so on to the power e, which of course becomes x to the ef plus e times something, right? I mean it's a multinomial coefficient, so there will be some stuff here and then x to the power ef minus 1, right? And basically this will be summation of things. So okay. Yeah, let me not try to compute that, it does not really matter, but this is equal to phi bar of x, right, and this means that so hence trace from L sub p to k sub p of alpha, this is equal to coefficient of x to the fe minus 1, I mean up to sign maybe, but yeah, or maybe minus of that, of x to the fe minus 1 of phi of x, okay. And so this means that p divides e implies that trace LP to k sub p of alpha belongs to p, right. Okay, so what have we proved? So we have proved that P divides E and alpha in O L implies trace of LP over KP of alpha belongs to P. And now this happens for all P above P. So hence hence this implies that trace of L to P of alpha, this is in P. All right. So now we are in good shape. Yeah. Okay. So now, but this thing is an if and only if statement. So okay. So what we want is P to the E divides this if and only if P divides E. Okay. So let's say P divides E, and then alpha belongs to OL. Okay. Okay, let me not write it this way. Let me take any alpha in. So let beta be in P to the minus E, and I let yeah, and so what I'll do is I'll let pi be in P minus P squared. So pi beta is in OL as before. So this means that trace of L over K pi beta, which is pi trace of L over K of beta, this is in OK, sorry, this is inside P. So hence trace L over K of beta belongs to OK. Hence beta is in L this inverse, hence P to the E divides dl over K. So that's one part. Conversely, if P does not divide E, then there exists alpha such that alpha in OL such that trace of trace from L to K of alpha is not in P, okay, and alpha bar generates OL mod P over OK mod P. Okay. Yeah, maybe let me just write it this way. Okay. And hence this is kind of easy. P to the E does not divide dl over K. Okay, fine. So as a corollary we get the following. We get this wonderful corollary that L over K is a finite extension of number fields P inside OL is ramified if and only if P divides the different of L over K, right. So if P is ramified, E is bigger than equal to 2, then P to the E minus 1 divides this, right, and E minus 1 is bigger than or equal to 1. Okay. So that's one way. Now conversely, if P is unramified, E is equal to 1, then P does not divide E, hence P to the E, which is just P, does not divide L over K. So we proved this corollary as well. Right. So in particular, here is a, so okay, so that's kind of fantastic, because now we know that if L over K is a finite extension of number fields, then only finitely many primes ramify in L over K. Okay. Of course, that finite set could be empty. So it may happen that there is no prime that ramifies in L over K, but we know that certainly infinitely many primes do not ramify in L over K. So up to this point we had no way of saying this. We can say it now because of this result that a prime ramifies if and only if it divides the different. So that's a very nice result. But here is another one which is kind of special to Q. So if K over Q is a finite extension and K is not equal to Q, then at least one prime of Q ramifies in K. And why is that? Well, we proved, so here is a proof of this, we proved that the norm from K to Q of the different ideal is the discriminant of K, right, and dk is bigger than 1 if K is not equal to Q. This was using Minkowski bounds. Hence dk over Q is not equal to OK. So there is at least one prime that divides this. So hence at least one prime divides dk over Q. So this situation is very different for other number fields. Now other number fields of course can have extensions that are unramified. If you only take abelian extensions, then there can be at most finite extension that's unramified. But if you don't put the condition of abelian extensions, then other number fields can in fact have infinite extensions also which are unramified everywhere. So this situation is very specific to Q, and you see why, because we are using these bounds on the discriminant. Okay. All right. So we proved this amazing result this time that only finitely many primes ramify in any given extension because they are characterized by whether they divide the different or not. And if you want to look at primes downstairs, then it's whether they divide the discriminant or not. Okay. From next time we will look at special examples of special fields. So we will study quadratic extensions, biquadratic extensions, cubic extensions and cyclotomic extensions. So all that we have studied up to now we will apply in these specific cases. Thank you.